channel. Yesterday in the last class, actually on Saturday, we have discussed about CPU scheduling, and then we have discussed one of the CPU scheduling algorithm, which is FCFS. We have just solved one questions. Today we are going to discuss FCFS also a bit more, and we'll see what was the problem in FCFS that we had to go. Scientists had to go to the next algorithm, which is SJF, which is the algorithm for the day of discussion. Okay, so yesterday in the last class we discussed about what is process scheduling, lot of different types of schedulers. We have seen three types of scheduler. We have seen, if you remember, long term, short term, medium term. Then scheduling algorithms, we started first come first serve. Okay, so today we are going to discuss about FCFS scheduling, a few more questions, little more details, convoy effect and SJF algorithm. Just confirm once if you guys are ready for learning today. If you guys are ready, just confirm in the comment box so that we can start the session now. I know you guys are done with your dinners, everyday activity is over. Now you can fully concentrate on your studies. Okay, I'm waiting for your comment now. If you guys are ready for learning today, just comment in the comment box so that we can start the very first discussion of the day. Okay, in the last class, I have given you this particular question as a homework. Yes, and I asked that just try to solve this question. In FCFS, when you run the processes, first come first serve, whichever comes first should be executed first. So if you want to make the Gantt chart of this particular given scenario, which process comes first? P1 comes first at 0 time. So at 0 time, we have an option to run a process P1. So when at 0 time P1 runs, it will run for 5 time unit just because its burst time is 5. Till 5 it runs. Now next, till 5, now we will check out the ready state processes. These 4 processes will come till time unit 5. So these 4 processes P2, P3, P4 and P5 will arrive till P1 executes in CPU. Arrive means will be added in the ready state, ready queue. Now among these, you tell me which process to run next. It's very easy. Whichever arrives first, this arrives first among all. Then P2 runs first. P2 runs next. After 5 time unit, it takes one more up to 6. Then remaining 3 processes P2, P3, P4, P5. Among them, which comes first? This one. P3 arrives. It will run for 2 time unit up to 8. Then P4 at 3 it arrives. So we'll run P4 next up to 12, and then at the end P5 runs 5 more time unit up to 17. Okay, now I'll give you a small detail. The small detail is what? Total for how much time processes are running. P1 running for 5 time unit. P2 running for 1 time unit. P3 running for 2 time unit. P4 4 time unit. P5 5 time unit. Total is what? 5 plus 5 10, 15 to 17. 17. So you can have one small verification of your calculation if here you did not make any mistake. How? If all the processes are running one by one, somehow no any free time is there for CPU. CPU is running all the time. Yes, 0 to 5 P1 was running in CPU, then P2, then P3, then P5. No any free time for CPU. Yes. So total how much time required to run all the processes? 17. Here is the 17. At 17 time unit, from 0 to 17, all the processes will be completed. So you can verify your answer like this. This is a trick. Nobody, actually not all the people will explain you this. Now the rest of the things are very easy. Completion time. P1 completes at 5. P2 completes at 6. P3 completes at 8. P4 at 12. And P5 at 17. Look at this. P1 completes at 5. P2 at 6. 8, 12, 17. Turnaround time. Completion time minus arrival time. 5, 6 minus 5, 1, 5, 8 minus 2, 6. 12 minus 3, 9. 17 minus 4, 13. Next, waiting time. Waiting time you will calculate by turnaround time minus burst time. 0, 5 minus 1, 4, 6 minus 2, 4, 9 minus 4, 5 time unit, 13 minus 5, 8 time unit. Rest, you can calculate average easily. There is no any issue. Yes? Okay. Fine. Now, the next thing is such kind of question. See, what happens, what we are learning right now is a very simple process to execute the processes, right? But sometimes it happens that to make you little uncomfortable, a question can be given like this, in which for a certain period of time, you will not have a process to run at all. So if CPU does not have any process to run, just because no process is there in the system, what CPU will do? Okay, I'll ask a simple question. You don't have anything to study, let's say. Assume that the day of gate examination, your study is over. No anything to study now just because gate exam is over. Next day, what you will do? Nothing to do. Fursat? Yes. Pre? Yes. You will do something? Anyway, you can engage yourself in some activities like going with your friends or playing, surfing the internet, etc., etc. It's okay, but study wise, no any study. Same thing happens with CPU. If no any process is there in the ready state, operating system will not schedule anything. So no any process is running, which means CPU is idle. CPU is idle means not doing anything. Look at this. Here arrival time P1 arrival time 5, P2 arrive at 8, P3 at 6, P4 at 3, P5 at 1, P6 at 7. Now if I ask you just make a Gantt chart. Yesterday in the last class I have explained you clearly that Gantt chart starts from 0. At time 0 we don't have any process. At time 0 we do not have any process. Are you understanding this? Look at this. When the very first process is coming, P5 is coming at 1. So when a process will come, then only I can schedule, na? Have you played game of cricket? In the game of cricket, let's say you are the captain, you are at the ground at 7 a.m. when the fixed time was there that okay, we will start the match at 7 a.m. tomorrow. The cricket match is between your team and neighbor team. Neighbor means some neighbor colony team, some other colony team. Now what? If you are at ground 7 a.m., your players are not at ground, can you start the cricket match? Okay, you can have the toss. Fine, you are ready to bat. Let's say you won the toss, you will bat first. But you need two people to bat, na? You are the one, but other fellow, who is there? Nobody is there. So can you play? Of course, nahi. Then you'll have to wait. In my era, so there was no any mobile phone also. We had to wait only. Kab aayega, when the fellow will come, when the fellow will come. And when fellow will come, that fellow will take a good shot from my end. Then after that, I'll give him bat. That was the scenario. Short means I used to beat. Yes, it has happened with me. Might have been possible. Happened with you guys also. So at time 0, no process is arrived. Till what? P5 arrives at 1. So 0 to 1, CPU remains idle. I'll show it by these blocks. CPU is idle. Ideally. Idle means CPU is not executing any process. Next what? At one time unit, P5 arrives and runs for 2 time unit. So P5 I can run for 2 time unit, 1 plus 2, 3. Okay, P5 done. And at 3 time unit, P4 can arrive. Yes, P4 arrived. So I can run next arrived process P4 at 3, which is running for 1 time unit done. Now at 4 time unit, do we have any process arrived? No. No. If we do not have process, again what to do? We'll have to keep CPU free, idle. So 4 to 5, 1 time unit, no any process is running. In that case, CPU again remains idle. Now next is what? This process done, this process done. At 5 time unit, this process arrives, P1 arrives. So P1 arrives and P1 runs for 4 time unit. I'll run P1 and it will run for 4 time unit up to 9. Why I am running complete process in single go? Just because FCFS is a non-preemptive algorithm. When a process gets the CPU, it will completely run, then only it will leave the CPU by its own wish. Okay, next, this process done up to 9 time unit. At 6, this has arrived. At 8, this has arrived. 7, this has arrived. So we have 3 remaining processes. All 3 have arrived. Okay, let's run them. Criteria, whichever comes first. This comes first, 6 arrival time. So this will be, this I will run next. Which one? P3. 3 time unit, it will run up to 12. Then next, at 7, this P6 arrives. 7 time unit, 12 plus 7 is 19. And after that, 2 time unit, P2 runs. It arrives at the end, 21. That's how processes will run. But my dear students, the previous trick will fail here. I told na, this will be summation of all burst times. Yes, this will be fail here. Why? Look at this. 4 plus 2, 6 plus 4, 10 plus 2, 12, 7, 19. Burst time summation 19, but I do have 21 here. Why? For 2 time unit, there was no any process in CPU. For 19 time unit, CPU was running the processes. Look at this, idle period 0 to 1, 4 to 5. 2 time unit idle, remaining 19 time unit processes are running, total 21. Are you understanding this? Confirm me please, so that you guys will not have any kind of trouble verifying your own question that okay, we got that particular concept, sir. Quickly, just let me know if you guys are understanding this or not. Come on. Okay. If you understood that remaining things, we can easily calculate how completion time P1. Now, when you run the processes and questions are like this, processes are not completing in the order that first P1 completes, then P2, then P3 and so on. No. That's why please be mindful. You'll say, sir, P1 completes at 3, P2 at 4, P3 at 9 and write in the sequence. Na, baba. थोड़ा दिमाग लगाने का है. You'll have to put your efforts and mind into thinking mode. P1 completes at 9. Just check out this diagram. P2 completes at 21. P3 at 12. P4 completes at 4. P5, sir, P5 completes at 3 and P6 complete at 19. Next, turnaround time. Completion time minus arrival time. 4, 21 minus 8, 13, 12 minus 6, 6, 4 minus 3, 1, 3 minus 1, 2, 19 minus 7 is 12. Just confirm if you guys are getting all the concepts. Turnaround time minus burst time is waiting time, 0. 13 minus 2, 11. 6 minus 3, 3. 1 minus 1, 0. 2 minus 2, 0. 12 minus 7 is 5. You can calculate average turnaround time and average waiting time also from here, and easily you can get the answer. Okay? Okay, fine. Next is convoy effect. See, what happens, I'm sorry. See, I have lived in a very small town named 𝐂𝐤𝐴𝐻. It is in Madhya Pradesh. There is a overbridge, and we have a lot of auto rickshaws in the town. You know what happens in that particular overbridge? If one auto rickshaw goes, which is very slow, of course, then all the cycle fellas, bike fellas, and car fellas are just going slow because of that auto rickshaw. So that auto rickshaw on that overbridge trying to climb that overbridge very slow. And then there is another auto rickshaw. This fellow is running with 9 km per hour. This fellow is running with 9.2 km per hour and trying to have a race with this, that I can go and climb before you. Of course, auto rickshaws, public transports are always in rush, but very slow. So it's climbing very slow, and because of that, all the fast moving vehicles, my car, my bike, every people are just stuck behind. What has happened? If a slow moving vehicle goes into this particular overbridge and climbing slowly like this, you might imagine at your place also it used to happen. Then in that case, you know what happens? The behind all the fast cars, fast moving vehicles, all those will be stuck behind and will go slow, and the traffic will move slowly. Okay, you can imagine there can be a Bharat, the marriage party on the road. Have you seen that? Possible, yes. There can be some other rally, maybe political, maybe regional, maybe some kind of spiritual, some kind of rally is there. If rally is there and those people are celebrating, dancing, doing something on the road, going here, behind that all the cars, bikes and everything is moving slow, long till long place, that particular traffic jam will be reflected. Happened? You have definitely seen this scenario in your city, town, village, everywhere. For sure, I'm 100% sure you might have seen this. So, you know what happens? What am I saying here? The thing over here is, if a slow moving vehicle or slow moving, political party or slow moving marriage party is on the road, behind that all the fast moving vehicles will also move slow, hence entire traffic flow becomes slow. That is the convo of that particular marriage party or something. Exactly same thing happens in the FCFS algorithms. In the FCFS algorithms, you know what happens? In the Gantt chart, if a very big process is scheduled first, it is moving slowly and executing at the end. Let's say the very first example which we have seen yesterday, P1 was having 24 burst time, this question I guess. P2 is having burst time 3 and P3 is also having burst time 3. P2 is having 3 burst time and P3 is also having burst time 3. Look at this. These two processes are executing just for 3 time unit, but we'll have to wait for P1 to complete, which is very big process. So if a big process is scheduled first, because of that big process, upcoming fast processes, small processes also will be delayed, and hence entire system becomes slow. Convoy effect. So I'll write certain things about this. If a big process is scheduled first, then it slows down system's performance. Why? Just because that single process itself is running for a long time and processor is not able to run any other process, and rest of all other processes are getting delayed. At the end, they are running for some time. That is called as convoy effect. This convoy effect happens only in FCFS. Only FCFS suffers from it. No any other algorithms will have this convoy effect. This is one of the very basic question that can be asked in 1 mark. Convoy effect, which algorithm suffers from convoy effect? Okay, fine. So these are some points about FCFS. Advantage: Very easy to implement. Whichever process comes first in the ready queue, we will maintain a queue first come first serve basis. P1 arrives first, we'll add. P2 arrives next, we'll add. P3 arrives next, we'll add. In that particular queue, whichever is the first process, the scheduler will schedule that process to run. Without any thinking, implementation is simple. If you understand data structure, if you understand queue data structure we will use here to keep all the ready processes. Simple. So easy to implement. Use queue to maintain ready. Maintain ready processes. Okay, great. No complex logic. Logic is not there. Whichever process is coming first, we will add it in the queue, and no any logic is required. Starvation is not there. What is starvation? Starvation is not that starvation which you suffer from every time. Hunger. If you had lunch, I ask, yes sir, I had lunch. Let's say right now I'm asking, you had your dinner? You'll say yes, we had dinner. But if I'll say, okay, I'll give you the treat, let's go, you can still eat more than what you ate in your dinner today. Still, that is what the starvation of engineers. I'm not talking about it. I'm talking about starvation of the processes. Starvation of processes means, is there any possibility that a process will wait for indefinite time? Indefinite means not the fixed time. For how much time process will have to wait to get the CPU? Is there any chance? No. Why? If process has arrived, that will be added in the queue. Before that, all the processes will run, and then after that, this process chance comes. No any problem at all. Here, there is no any chance of starvation. Why not? Just because all the processes will get the fairness. So no starvation, which means we implement fairness here. Each process gets the fair chance. We are not choosing or favoring some processes that we will favor these type of processes, but these type of processes will keep in waiting. And that's why starvation may occur. Here, there is no any such kind of problem. Okay. I'm good, Diplav. Thank you for asking. How are you? Okay. What are the disadvantage? One is preemption is not there. Once a process is given to CPU, it will completely run. No any preemption is allowed here. Next, convoy effect makes the system slow. That is another disadvantage of FCFS. Okay, next is shortest job first. To solve this problem, convoy effect, SJF was introduced. SJF says that, okay, if you are saying that if you are scheduling a if you are scheduling a very big process at first place, because of that system is becoming slow, okay, let's schedule the small process first. Let us schedule small process first. Okay, if small process is scheduled first, then what happens, sir? In that case, system's performance will not become slow. Small processes will run first, quickly. System will not become slow. Yes. So what happens? SJF is that algorithm which says, okay, I'll have to write scheduling criteria here. Scheduling criteria is smaller burst time process first. The process which is having smaller burst time should be scheduled first. But what if two processes are having equal burst time? What if two processes are having equal burst time? In that case, tiebreaker is to be used. Tiebreaker is what? Tiebreaker is FCFS. So please be mindful here. I have given this information. Even though you remember, but still you make mistakes. I have seen thousands of students doing this. When I say FCFS, you don't talk about process ID first now. If two processes are having equal burst time, you will have to check out the arrival time first. Which process is having arrival time smaller? Whichever process arrives first should be scheduled first. If two processes are having arrival time also first equal, then you'll have to check the ID. So in this case, what will be the sequence of checking? First of all, burst time. If burst times are equal, then arrival time. If arrival time of two process also equal, then you'll have to check the process ID, and process ID definitely will not be equal for sure. What is the type of algorithm? This is also non-preemptive. Once a process is scheduled to run on CPU, it will run. I remember my son here. He's just 8 month old, but when he commits that I will take this, grab this particular toy and I will take that thing in my mouth like this all the time. Whatever I give him, he just eat, 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 eat. It means just take it or take to his mouth. Same thing. Commitment done, process will completely execute. Okay, next thing. Let's solve this question now. Same question we have solved yesterday for FCFS. Now we are solving it for SJF. In SJF, always remember, please always remember, we can schedule only those processes which are already arrived. We can schedule the process only that one which is already arrived. Okay, let me give you a simple example. Simple example. Let's say you decided that along with your team, you will have a game of cricket tomorrow morning 7 a.m. in the ground with neighbor team or neighbor colony's team. Fine. In the morning, when you reach to the ground 7 a.m., only two members reached, you and one of your friend, who is not the best batter of your team. He is average, okay. I can send him to bat at the end, maybe after 4 or 5 wickets, but not initially for sure. Now you tell me, if let's say the neighbor team is completely over the ground and that neighbor team is pressurizing you, have the toss, have the toss, have the toss. Okay, you have the toss. And let's say you opted for bat first. You won the toss, you started batting first. Now what happens when you started batting first? Two members, you and your friend, batting started. Your friend is not the best player of the game, but still you made that fellow to play. Why? Just because there was no any option. You had to play the game, yes, and your another best player is not at the ground. Now after some time, let's say few members have come and your another friend who is an average player got out. Then among whoever have come on the ground, you will choose the best batter and you will ask, okay, you come for the batting. Can you schedule a person who is not on the ground? Can you ask the person that this fellow only will bat? Let's say one of my friend, his name is Krishna, that is the best batter of my team. He is not at the ground right now. I don't know where he is right now. When he will arrive on the ground, I don't know. Can you ask that fellow or can you ask the opponent that Krishna will bat next? I don't know where the Krishna is. When he will come on the ground, I don't know. How can you schedule that fellow? No, I cannot. So remember, I'll have to understand what processes have arrived already. Look at this, arrival time 000. All processes have arrived at time 0. Means I do have three processes P1, P2, P3. Among these three processes, I'll have to schedule one based on burst time. Which process takes minimum burst time? These two. Equal burst time. Okay, then I'll go with the arrival time. Arrival time also equal. Then ID. Based on ID, P2 runs. P2 is smaller, P2 runs. P2 runs for 3 times. Okay, done. Now two processes still remaining, P1 and P3. Now which process I'll run? Smallest process first. Smallest is P3. So P3 will run next. Up to 6. Then at the end, P1 will run for 24 time minute up to 6 plus 24, 30. Are you guys okay with this? Can you please confirm quickly? Confirm re baba if this is okay for you or not. Completion time. Just check out the completion time. P1 completes at 30. P2 completes at 3 and P3 completes at 6. Turnaround time, completion time minus arrival time. 30, 3 and 6. Waiting time is turnaround time minus burst time. 6, 0 and 3. 30 minus 24, 6. 3 minus 3, 0. 6 minus 3, 3. You calculate the average here. I want it. Average turnaround time. 30 plus 3 plus 6 divided by 3. 13. And what is the average waiting time? 6 plus 0 plus 3 divided by 3. 3. You know, when you have run P1 first, then P2, then P3, your average turnaround time was 27. And your average waiting time was how much? Average waiting time was 0 plus 24, 27, 51. 17. Average waiting time was 17. Average waiting time now is what? Just 3. Average waiting time is just 3. And at that time, average waiting time, average turnaround time is 13. At that time, it was 27. Average waiting time in the FCFS was 17. Here is just 3. How is it possible? How is it possible? सर ओएस कब तक खत्म होगा बेटा? अभी ये शॉर्ट सीरीज है. It will be just a short series. Once if more number of members will be having good commitments over here, I'll continue this. Right now I scheduled CPU scheduling algorithms, first module of this, and that will be till next week. So here is what SJF is minimizing the average waiting time. How? Just scheduling the small processes first so that next process comes quickly in the CPU and hence waiting time reduced. Okay, now you try this question. Try. You try this question once. I'm giving you this question, you try it. I know number of processes are so many here, but you will learn. Are you guys able to solve this? I am waiting for your answers. If you are stuck at some place, you can let me know. Remember, I have already told you, whichever process has already arrived, Among them only you will have to schedule a new process or schedule the process on the CPU. You can't schedule the process which has not yet arrived. Otherwise, gadbad ho jayega. There will be a problem, boss. Okay, somebody is saying first P5. How is it possible? P5 process arrives at 5. Gantt chart starts at 0. My friend is arriving at 5 minutes, 7:05. At 7:0, can I tell that my friend P5 will play next or will go for playing next, will go for batting next? No. Right now, the thing is at time 0, all of them has not arrived. P2 will arrive later in future at 1. P3 will arrive at 2. P4 arrived at 4. P5 will arrive at 5. P6 will arrive at 6 and P7 will arrive at 8 in future. At time 0, what process I have in the ready state already arrived? You tell me at time 0, only P1 has arrived. Only one process has arrived. So if only P1 has arrived, I'll have to run P1 first. Why so? Just because there is no any other process right now arrived. I cannot see the future, Re Baba. That P2 will arrive at 8 or will arrive at 1 or something. No, whichever has arrived, I'll have to schedule that. So P1 already arrived at 0. I'll have to schedule it and it will run for 6 time unit. Why 6 time unit completely, sir? Just because it's a non-preemptive algorithm. When non-preemptive, when a process is given to run, it will completely run. Now what? Now, sir, up to 6 time unit, P1 will run up to 6 time unit. Arrival time till 6, all these processes will arrive. Among these processes, now I do have a choice. I do have choices now. Choice is what? One process you can select, which is having minimum burst time. Sir, last time to you didn't even check the burst time. Last time I was having only one process. P1, only one process in ready state. So that process I have selected without any criteria. Criteria needed only when we have multiple process. Nah. If only one process is there, what is that criteria? You have only one dress to wear for, let's say, a particular party. You don't have to think like, okay, this particular color will suit me or not, this particular party will have this appropriate or not, if I wore this particular dress before or not, doesn't matter. I do have one cloth, I'll wear it and I'll go, no thinking at all. But if I do have 25 cloths to go to the party, I'll have to make the criteria. This one too bright for the evening, this one too heavy for this party, this one too classy for these people with whom I'm going for the party, this one I have already wore in front of these people, this one, okay, I can wear this particular party, this particular dress. So criteria is to be needed when you have multiple things to schedule. Here also look at this, these many processes we have. Among them you can choose the smallest one, which is the P5. P5 will be scheduled one time unit up to 7. Till 7, P7 arrived? No, not yet. So now what are the processes remaining? This is done. This is done. 1, 2, 3 and 4. These are remaining still. Among these, which one is the smallest one? P4. I can schedule P4. Up to 9 it will run. 2 time unit. Now till 9 when P4 will be running, at 8 P7 arrives. When P7 arrives, yes, that is the smallest among remaining 4. 3, 4, 5, 2. 2 is the smallest. P7 will run for 2 time unit up to 11. Next P2 runs for 3 time unit 14. Then remaining 2 P3 runs 4 time unit 18. 5 time unit 23. P6 runs. Is there any idle period here? No. So I am just reconfirming that if I have made all the calculations correct or not. How? Look at this: 6 plus 4, 10 plus 3, 13 plus 2, 15, 16, 21, 2, 23. Yes, 23. Till 23 I have run. One of the confirmation I made. Now resting is easy. All same to same. Once Gantt chart is done, then resting is easy. Just confirm if you guys understood this. P1, when P1 completed at 6 time. P2, 14. P3 completed at 18. P4 at 9. 5 at 7. 6 at 23. And P7 at 11. Next. Turnaround time, completion time minus arrival time: 6, 13, 16, 5, 2, 17, and 3. One last, waiting time. Waiting time is turnaround time minus burst time. 6 minus 6, 0. 13 minus 3, 10. 16 minus 4, 12. 5 minus 2, 3. 2 minus 1 is 1. 17 minus 5 is 12. And 3 minus 2 is 1. हम सर इसी वालों के लिए आप पढ़ाएंगे इंजीनियरिंग सर्विसेज के लिए? बेटा अभी तो सतीश सर पढ़ाते हैं इंजीनियरिंग सर्विसेज वालों के लिए. सतीश सर हैं जो इंजीनियरिंग सर्विसेज के लिए पढ़ाते हैं. Now resting is very easy. If you want to calculate average waiting time and average turnaround time, you can do it. Average waiting time, average of all these: 0 plus 10 plus 12 plus 3 plus 1 plus 12 plus 1 divided by 7 processes are there. Just calculate how much it is. बेटा मुझे आइडिया है नहीं कि सतीश सर क्या पढ़ाते हैं, क्योंकि मैं भी अभी अभी सिस्टम से जुड़ा हूं. 5.57. ठीक है. This is average waiting time. Average turnaround time will be 6 plus 13 plus 16 plus 5 plus 2 plus 17 plus 3 divided by 7 processes. 6 plus 13 plus 16 plus 5 plus 2 plus 17 plus 3 divided by 7, 8.85. Approximately 6. This is how you will get the answers. Okay, fine. Now, another example. See, when you were a kid, let's say your mom sent you to purchase some item from a shop, very small shop, but very busy also. Small kid. You are having some money in your hand and asking the shopkeeper, but shopkeeper cannot concentrate on you. Why? Just because you are this much of kid and big adults are already standing in front of you or around you, and your hand is not even reaching to that guy. You want to have some kind of idli, samosa, or some toothpaste or something you want to purchase, some ice cream, but your hand is not visible to that fellow shopkeeper. People are standing next to you. You are waiting. This fellow will go, this fellow will go, then I will be visible to the shopkeeper. So shopkeeper giving them their ice cream, etc., whatever the item is. When they go, meanwhile other fellas are coming and keep coming. You are standing. Please give me one ice cream, chocolate ice cream. Nobody is listening to you. What is happening? Indefinite waiting. Your waiting time is not fixed till when these all people will go, so that you will alone will be here. the smallest fellow, but still the shopkeeper can see you and you can get the chance. That is called as a starvation. The shopkeeper is favoring some kind of a people, and those are the taller fellas, so that the smaller fellas, the smaller fellas like you, the small kids, the shopkeeper cannot see, and hence you are getting into starvation. So what is starvation? Starvation is here. If let's say there is a process, this process, let's say this process having burst time 5, but that particular process in my system getting CPU at 18, but before 18, let's say at this point of time, P8 arrives at 9, burst time 2, P9 arrives at 10, burst time 3. Like this, new processes are coming, arriving, and those processes are having burst time lesser than 5. This process will not get the chance to run on CPU. Why? Just because the smaller processes are keep arriving. Smaller processes are arriving, and because of that, a big process, maybe multiple big processes will have to wait for how much time? When these arrival will stop, then only that big process will get the CPU. So we don't know when. In that case, indefinite, not fixed, not definite kind of waiting time is there. For which one? For this process, and hence it is called as starvation. So this SJF suffers from starvation. Yes, true. Okay, so SJF is having disadvantage. Longer processes may suffer from starvation. Look at this. Second problem is preemption is not there. Look at this. A big process arrives at 0, scheduled at first. Later on, at one time unit, a smaller process came. P1 cannot be stopped in between. P1 will complete till 6. Look at this. Even though later on, at 5 time unit, P5 arrives, which is even smaller. At 4 time unit, P4 arrives, which is smaller. But then 6, of course. But we could not preempt P1. That is the another disadvantage. And the biggest disadvantage is we cannot implement it practically. In operating system, when we actually build the operating system, we cannot implement it. Why? To implement this, we need to know that these processes will have how much CPU burst time, and practically it is not possible. What are you saying, sir? Okay, I'll ask a simple question. If you have opened WhatsApp in your phone, or let's say web browser in your laptop, can operating system know till when you will run that application? Till when you will keep open that WhatsApp or web browser? 1 hour, 2 hour, 5 minutes, 10 minutes, 5 seconds, how much time that particular web browser you will keep open? No, just because it is user dependent thing, operating system cannot know it. So a process will run on CPU for how much time unit? Operating system cannot know. Hence, these burst times are not actually practically known for a process, and hence no practical implementation because burst time is not known in advance. Now you'll ask a question, sir, then why are you practicing these questions with us? Why you have given this question? Why somebody has given this algorithm? This algorithm came into the picture from a study. The study says that if, let's say, in last 1 hour I have executed these 7 processes, their burst times were like this. If at all I will execute these processes in their sequence of burst time, smaller burst time process first, then next, then what will be the average waiting time? Let me calculate it. So from past data, whatever I have taken, I calculated average waiting time, and among all the non-preemptive algorithms, SJF is providing you minimum average waiting time. So SJF is that algorithm which is the standard algorithm, or I should say the benchmark algorithm. This is the benchmark, the ideal benchmark algorithm. So whatever benchmark algorithm is giving you average waiting time, if any other algorithm can get the average waiting time around it, then we can say that, okay, that other algorithm which I can implement practically, I will use. Why? Just because it is very near to the idealistic situation. So we discuss it for the benchmark discussion. So benchmark is something like average waiting time and average turnaround time, both. Also average turnaround time also. Among all the preemptive algorithms, this SJF provides minimum these values. So if in the question such scenario given, not given that this particular scenario I'll have to execute with which algorithm, FCFS not given, SJF not given, no any algorithm given, and they are asking what is the minimum average waiting time for the running these processes for non-preemptive algorithm, boss, you will have to use this SJF algorithm without even they have given you the algorithm name. Why? Because of this point. Next is better throughput in continuous execution. So when processes are keep coming, and you are running, in that case, what happens in first 1 hour, how many processes you can execute is throughput. More you can run. Why? Sir, why throughput? Throughput is nothing but number of processes executed in 1 unit time. Number of processes executed in 1 unit time, 1 hour, 1 second, 1 minute, like this. So if you will run smaller processes first, you can execute more processes in the lesser time. And that is what gives us an idea. In GATE exam also we'll have to do the same thing. We'll have to take that question first, which takes lesser time. If some question is taking more time, you just leave for at the end, so that in first 2 hours we can solve maximum number of questions and we can be confident, okay, now my GATE rank is secured. Now later on, whatever big questions I am having, I can solve them later, so that I can even increase my marks and I can target the top rank. Okay, so these are some points about SJF. When no preemption is there, solution of this is SRTF. SRTF is what? Shortest remaining time first. That algorithm is nothing but the preemptive version of SJF. It says that we will run the process with the minimum burst time. But if any process is running right now which is having bigger burst time, and later any new process arrives which is having lesser burst time, then I can stop this process. I can stop this process. Like if I have sent a particular cricketer to bat just because that was the only available option in the ground. Now that fellow is playing but very slow. And some player comes after some time and that player is better. So I'll say what? Okay, you retired. I will send you for batting later. You retired. You are playing so slow. You retired. This fellow will play. So retired hurt or retired, however. Why? Just because that player is slow. I don't want that player. That player can make my team lose. That's why retired I will send you later. New player which is better one, faster one, can score quickly runs, I will send that fellow for playing. So that is the SRTF algorithm. We'll see that particular algorithm tomorrow. We'll discuss it in detail how the questions are solved. SRTF is little complicated, not much Rababa, little complicated, but I'll explain you how to solve that questions. With 4-5 practice questions, we will understand SRTF tomorrow in the evening. Okay. I'm sorry. Thank you so much for joining this particular session. Please come tomorrow with little bit of revision of today's class so that you can enjoy tomorrow's class and you can relate it tomorrow. See you tomorrow at the same time, 9 p.m. Thank you so much. If you have any doubt, query, question, keep posting in the doubt so that I can pick it up from there. Thank you. Good night. Happy learning. Bye-bye.